Welcome everyone. Today we're going to talk about the parallel axis theorem. This is a pretty straightforward concept, but we just need to introduce it because it may come up when we talk about, we look at rotation, angular momentum, and torque. So we just need to know what it is, know how to use it. It's very straightforward. Let's get it started. So the basic concept here is that if an object rotates around an axis parallel to its center of mass, the total moment of inertia is the object's inherent moment of inertia plus md squared. So that's the mass, where d is the distance from the center of mass to the new axis of rotation. So normally, we calculate the moment of inertia of an object that is rotating about its center of mass. So if you're ever given a moment of inertia, that moment of inertia is valid if the object is rotating around its center of mass, and only if it is rotating around its center of mass. However, if we are given that moment of inertia and we have a new axis of rotation, we can use this parallel axis theorem where we take the normal moment of inertia and we add the mass of the object times the distance from the center of mass to the new axis of rotation, and we've got our new moment of inertia. Could not be simpler. So how about this? How about a sphere that is rotating around a new axis in the counterclockwise direction? So instead of spinning, right, spinning around its own axis, we are now spinning a distance. So say we have a sphere like this and it's on a string and we're spinning it around our head. That would be an example of the type of situation that we would have here. So the given moment of inertia of a sphere is 2/5 mr squared. And I should have mentioned that when it says ICM, that means I center of mass, so the moment of inertia around the center of mass. So let's say if we have a mass of capital M, draw an M to save my life, and a radius of capital R. Okay, so let's figure this out. What is the new moment of inertia? So we have I total is equal to ICM plus MD squared. Really straightforward. We are just going to use the I total equals. Okay, so the moment of inertia around the center of mass is 2/5 mr squared plus the mass, which is capital M, and then the distance to the center of mass they've already given us. So it's the distance to the center of mass, so the axis that goes through the center of mass, not the distance from the surface of the object to the new axis. Not that distance, but this distance. This should be a y, yes. So plus m, and then that distance is just going to be d squared. And that is it. And that is it. We just add those two moments of inertia together and we get the new moment. So, a person is spinning a frisbee on the tip of their finger at a constant angular velocity. So let's start where you're going to say omega 1 is capital W, and then slides it so that they spin it with their finger at the lip of the frisbee. We want the change in angular velocity. So we're saying that the initial angular velocity is capital W. I'm going to say that the mass is capital M, and the radius is capital R. So let's figure it out. First, we're going to use conservation of angular momentum here since we're changing our system, but angular momentum has to be constant. So the moment of inertia initial is 1/2 capital M capital R squared. So we get that from this formula, 1/2 mr squared. And then our initial angular velocity is capital W. So that means we start with moment of inertia initial multiplied by capital W. So that means we have times capital W here. And this is the angular momentum initial. This is going to equal I final omega final. So how do we find I final? So I final, well, let's think about the situation here. What have we started with? We started with a frisbee spinning around its own axis. And what we end with is a frisbee spinning around this axis. So the distance from the center of mass to that new axis is going to be the radius, capital R. So using the parallel axis theorem, we add the moment of inertia around the center of mass, which is just the moment of inertia of the disk itself, 1/2 m capital R squared, plus the mass of the object, another capital M, and then the distance is R squared. So lucky us, we can combine these terms, and our final is 3/2 mR squared. So that means that if we look back up here, we have 1/2 mR squared capital W equals 3/2 mR squared omega final. So it looks like we have a lot of canceling that we can do. This 1/2 will cancel with this. Mass, mass, radius squared, radius squared. So we're left with W is 3 omega final. That means omega final is 1/3 W. However, we're not done. What I asked for is the change in angular velocity. So that means omega final minus omega initial, which is 1/3 W minus W. So we get a negative 2/3 W is our change in angular velocity. So that's a very basic example of the parallel axis theorem. If you have any questions about it, come see me. We just need to know that we can adjust our moment of inertia if we rotate around a new axis. All right, thanks for watching.